So, okay, before starting before moving to the new topic of the next module, I'd like just to check a couple of examples, very simple, on the use of these identification recursive identification approaches, because it's something that is not yet implemented in the system identification toolbox, because the system identification toolbox is implementing offline or batch identification approaches. If you want to use an online or adaptive, you need to perform some use different blocks in Simulink, as we will see in an application of a adaptive controller, a simple adaptive controller. So now we will examine the case in order also to comment or to remark some properties. Two application examples in MATLAB. The first one is in lecture 3.5. The first one is a script that is comparing the use of AREX with recursively square, and also the use of different identification inputs, and also how to perform a simulation, because it's something a little bit more complicated than static or a batch or offline identification approach. So let's download from lecture 3.5 the file which is called lecture 3 exercise 2, and from lecture 3.5 lecture 3, the next one, lecture 3 exercise 1 is something that is not really used for the exam, but just for understanding and implementing and checking some how to design an experiment, an identification experiment. Then let's go in MATLAB and let's try to open the first script. It's a MATLAB, where it's quite simple. I'm going to comment it. Is here. So just a very quick introduction to the variables. It's very simple. So we are using a number of samples equal to 5,000. Here you can see some commands in order to generate signals. For example, I'm using the function rand_n for generating a Gaussian noise with the standard zero mean, normally zero mean, and standard deviation 0.1. This should describe the estimation error when we are simulating our RX model. And here is this is a transformation, just you don't really to do it, but it's just if you want to be sure that, if you want to guarantee that your signal is zero mean and standard deviation 0.1, so what you should do, you remove the mean value of the signal, so you are sure, you are guaranteed that the signal is zero mean, and you multiply the standard deviation you want, because normally this Gaussian noise should be standard deviation 1. So in order to have a standard deviation 0.1, you need to multiply by the standard deviation you want to obtain. And this is an interesting function, because this generates a pseudo-random binary sequence of length n, so with n samples, with the standard deviation between 0.1 and with values between 0.1. So you can play with this function in order to obtain different characteristics for your sequence. Then I simply defined the middle of your time when you have a change in the parameter. Then I just defined some auxiliary signals, and here we have the change in the parameters. So the A1 parameter, which is the parameter of the RX model, which is changing from 0.8 to 0.2, and the B model, the B vector modifies from 0.5 to 0.1. Then I generate the theta, what we call theta star or theta 0, which is the theoretical value of so the real value of the parameters. And then this is the way for simulating a model, an RX model. So I define a deterministic, deterministic transfer function of your RX model and the stochastic transfer function, and then I'm using this function LSIM, the linear simulation. This allows you to simulate a given model provided its transfer function with respect to its input. This is the deterministic input and this is the stochastic input. So of course, the whole simulation is given by the summation of the two inputs. So not the summation, the first input and the second input of the model. One before the change and the second model after the change. Then once we have generated the data, so I just replicated, I just used if you remember the values of your example, I generated the matrix P0. You remember P0 is the initial value, is the initial accuracy of your estimation vector. Theta 0 is the vector 0. We can modify lambda. Let's try with lambda, for example, 0. This is an example, let's try 0.99. This is the forgetting factor. In order to implement the recursively square, you have the function recursive RX. This is the function provided in MATLAB that is used for estimating a recursively square. And you can see here, if you define of course, if you need more information, other details on this function, just type help RAX and you have all information you need. This is the basic use if you want to use it. So as you can see here, RAX, you define, you simulate a model with the input and the output. The order is order 1. And here you are saying, I'm using a forgetting factor of value lambda, and the initial value of the simulation of the recursively square is theta 0 with given accuracy, initial accuracy is P0. So this is the implementation of recursively square algorithm. And then there are some other, maybe you can be interested in this, in other function. This is a function for estimating a model with the classical least square, just provide the inputs and the output and the order. So this estimate a model, RX model, and with this function, RX data, it extracts from this structure, MRX, it extracts the polynomial AB, if you remember, of your model, and also the accuracy of the parameter. So you have the vector of the accuracy. So you know if the entries of this vector, of these polynomials are accurate or not. And then here I perform some simulations. So you can, for example, in this example, you can play with your lambda. So let's try with the value 0.99. And you can see, for example, here that you can notice that the tracking capability is very slow. It takes about, you can see here, about 500 samples to track, to understand that there is a change, and to track, to follow the right parameters. But try, for example, let's try to change, let's try 97. If you remember, is the recommended value for your lambda. You can see here that 97 perhaps is not, because it's not very appropriate, because if you see here that the parameter A is very inaccurate, you see that, you may notice that the tracking speed is higher, so the estimation is very fast, but the actual estimation is very accurate. So it's fluctuating around the real value of your parameter, and perhaps you are not so good, and you put, let's see, 0.7 because you want a very fast, a very quick algorithm, and you can see that it's very, if you notice, the parameter A is very noisy. So you cannot even distinguish between its value before the change and after the change. So you see, you can notice that of course, here is more evident, is more clear, is clearer, because the deviation of the parameter is higher. But here, because the deviation of the parameter is not so high, so the noise is hiding the value, the change, so it cannot be distinguished. So it means that you need to perhaps consider a trade-off between the tracking speed and the accuracy of your estimation. So it's why in this example, perhaps there is no best value, but perhaps the recommended value is in the note here is perhaps 98. It's a good trade-off between the speed of your. Of course, it depends on your application. So perhaps it's quite good, because you see here that the delay is about 300 samples, and also the accuracy, of course, is not. It depends on the noise, on the signal, but is quite. And I don't know if you want, for example, to see what happens if you reduce the standard deviation of the noise. So you put a noise which is smaller. Let's see what happens. You can see here that also the accuracy of your estimation is better, because of course it depends on the signal to noise ratio. So it's very interesting, this fact. You can see here that the estimation of your recursive algorithm is smoother with respect when the noise is lower, because the uncertainty of your estimation is directly depending on the level of the noise. So you can play with these examples. We have a second example, is a little bit more complicated. I don't want to. It actually comparing we are using 1,000 samples. We are generating the same equation error, but we can play with the signals that are used for the identification. If you remember, the pulse signal is the worst for the identification because it's not persistently exciting of any order. So there is no way for obtaining an estimate of your parameter. So if you put, for example, you can put 1 here in order to enable the generation of a pulse signal, or a square wave, as in the example, or if you put 0 in both these Boolean values, you have a pseudo-random binary sequence, which is the optimal one. And another analysis that I'm performing here is that I can generate the data with a Rmax model, which is more complicated rather than an Rx model. So you can generate an Rmax model, the data with an Rmax model with an Rx model. So of course, then you have your simulation, and you can perform a recursively square estimation. And depending on the selection of the right model, it depends the characteristics of your estimation. For example, let's try to select, for example, a pulse signal, which is the worst signal that we can use, we can consider. And for example, of course, let's try 0.98 with your lambda, and we are considering an Rx model. So you can see here that you can see here, for example, that at the beginning the signal is not persistently exciting, so you are not currently estimating anything, so you cannot see anything here. And then you are estimating the parameter, for example, here, which is not very good, but is an estimate of your value. And so you can select to change in a better signal for your identification. So perhaps a square wave is a little bit better. Let's see what happens with the square wave. You can see here that now the estimation is improved. Of course, you can see here the effect of the noise, but at least after an initial transient, you have an estimation of your parameter. Of course, it depends on the level of the noise, so your your estimation is fluctuating around the value of your parameter. Let's try to, for example, if you put both signals, both the variables 0, you are using the best input ever, which is the pseudo-random binary sequence. And in fact, the estimation, let's see the estimation of your parameter, is a little bit better. You can see here that is improved. You can notice that when from the previous simulation you have some a little like a periodic change in your estimation, but the pseudo-random is a little bit better. And another, for example, a phenomenon that you can observe, of course, you have a noise which is quite high, because if you can see here, the noise was very 0.5, which is very high. So if I put 0.1, which is the level of the previous noise, and I run again our estimation, we see now that the level, your estimation was closer to the real value, which are quite good accuracy. And as another example, I leave the selection like this, but now I try to generate the data with an Armax model. So it means that the model that you are using for the identification is not the same model that generated the data. And let's see what's happened. As you can imagine, the results of your identification is not as for the case you had before, because you can see that your estimation is worse than the previous one, because the model that you are using for your estimation is not the same that of the model which generated the data. So you can see that there is like a bias in your estimation. So normally you should assume that the model that generated the data is the same of the model that you are using for the identification, at least as an assumption. On the other hand, you are obtaining a estimate which is not consistent, so it is biased if the structure is not the same. So you can try and play with these two examples. And we will see in the next lectures how to implement these estimation approaches for the derivation of an adaptive controller, which is one of the possible ways of generating an adaptive regulator. I want just to start, and the next time